So I made a table. This doesn't have the transmission line stuff on it. I'll try to get that typed up, but I did have this table of stuff relevant to this chapter. So on the first, this is all in the book, at various points, but I just tried to collect it together here on one page. So the coordinate system conversions we talked about, last time, converting coordinates and then vectors. The vector conversion, he has the little tables showing the dot products with the vectors. Instead, I think you're going from Cartesian to cylindrical. The A row component would be cosine phi times the AX component plus sine phi times the AY component, and then so on for the other three. So instead of using that table to figure them out, it's got them all explicitly. And then it's got some vector identities. I think these are in one of the appendices in the back of your book. It's got these vector identities. You see this upside down delta thing. I don't know if you've seen that before. We'll see it today for the first time. It's called the Dell Operator. So we'll use it as we talk about the gradient and also the divergence of a field, and then we'll see it again when we talk about the curl. And then probably most useful on the back, and again, these are all in the appendix, is a series of vector operations. And you'll see it's got the differential length, differential surface, and differential volume elements in the different coordinate systems. But it's also got the gradient, divergence, curl, and Laplacian, and they have different forms. They look pretty nasty. We'll look at a couple examples today to hopefully convince you that they aren't perhaps as nasty as they appear. I went off and left home this morning without bringing my lecture notes, which I was working on last night. I think I left them on my desk at home. So I'm not going to cancel class, so we're going to I'm just going to try and, since the book is online, reference the book here and work through. So the first section is on the gradient, and the gradient is an operation that you do on a scalar field to produce, and it produces a vector field. So you'll see the electric field intensity is a vector field. Voltage is a scalar field, doesn't have direction. It's like temperature. There's no direction associated with voltage like there is the electric field. But the electric field is the negative of the gradient of the voltage or potential. So, but it's defined as this operator. It's called the Dell symbol or Nabla symbol, but the x-directed component is the partial derivative of the scalar field with respect to x, plus the y component is the partial derivative of the field with respect to y, and then finally the z component. It takes a fairly simple form in Cartesian coordinates, but remember these are all changes, rates of change with length, partial depth with respect to x. And in the Cartesian and spherical coordinates, we have some of our components, phi, for example, or in spherical, both phi and theta, that aren't distances. And so those gradients definitions in those coordinate systems look a little different. They're not just theta partial depth with respect to theta, because that doesn't give you a distance. So those are on that handout, the definition of the gradient in these different coordinate coordinate systems. And we can look at an example. But just to try and give you, well, it is helpful to, we'll see this thing, this Dell symbol, it's called a Dell Operator. And it's actually defined. So it's not a complete thing, right? This symbol represents, it has to be applied to a function or a vector. We'll talk about those different applications. But right now, this operator is applied to this function, partial with respect to y. So it's more of a memory aid than anything else. So we will use this not only for the gradient, but also for the divergence and also for the curl in Cartesian coordinates. It's not as helpful as a memory aid and the other coordinate systems. But if you remember this for Dell, then the gradient of a scalar field is just Dell times F, really. Again, it's not really multiplication, you're really taking derivatives here of that corresponding function. And to kind of give you an idea of what this might look like, let me just draw a picture in the XY plane. And let's say, let's say we've got temperatures, I'm going to say it's pretty cold. So, maybe 0 along this line, and maybe 10 plus 10 here, and then, maybe, well, whatever this location is, maybe I'll say it's minus 10 here, along this line. So if you can imagine this as being a temperature field, the gradient is the change in temperature with distance. So in this case, the maximum rate of increase in temperature is always to the right. So the corresponding gradient of this field, and I could roughly, I could read what we're really talking about here is, this temperature corresponding to the graph I wrote is something like 10x, right? If I call that 1 and this minus 1, that equation would match actually that plot, right? And at 2, it would be 20 degrees, let's call this Fahrenheit. It means it's really cold. Okay. But the corresponding gradient is this vector field that always points in the maximum rate of change. In this case, it would be to the right. And then the magnitude would be, in this case, it would be 10 degrees Fahrenheit per 1 meter. So, by just based on our definition, the gradient of 10 here should be its x directed, and that would just be 10. And it would have units of degrees Fahrenheit per meter, would be the corresponding gradient. The definition should give us that. If you look at the definition, we need these 3 partial derivatives going with respect to t. The partial t with respect to x is 10. The partial t with respect to y is 0. The partial t with respect to z is 0 because it doesn't depend on y and z. It only has this x-dependent component. And then, so that means delta t would be looking at this definition. This is 0, this is 0. It's just x bar 10. And kind of in agreement with our new intuition about what this gradient is meant to signify. So that there's really 2 components of the gradient. He talks about it here in this little box. The gradient is this vector that points in the direction of maximum change. So if you think about, if I, instead of temperature, if I had this like elevation in feet, a contour map or something like that, where it's 0 feet above sea level, 10 feet above sea level. So if you could imagine just a hill, the gradient is always going to be pointing toward the steepest part of the hill is always going to be pointing up the steepest part of the hill. The other direction will always be the maximum rate of decrease. Okay. So the vector always points in the maximum, wherever the scalar field is most rapidly increasing, it points in that direction. And the magnitude is that maximum rate of change. You can get the rate of change in other directions by actually just dotting this with unit vectors pointing in other directions. Like the rate of change in the y direction we could get by computing the dot product, doing this vector projection of this onto a y unit vector. But x dot y is 0. There is no rate of change in this particular case in the y direction. So, another example, and just for visuals, kind of a visual sketch. Let's take a donut shape, but it's not really a donut. It's just a circular ridge, around the origin. And let's say it's going to be 0 there. And then, at some radius 1, let's say it's 5 feet high. And this thing is, again, it's a ring. And then the distance here, let's call the distance 1, although my elevation is 5 feet. And it could be smoothly varying between 0 and 5, and then it goes back to 0 at 2 meters. Okay, let's say in a ring. In that case, the gradient would be pointing always in the maximum rate of change. Now, if it's going back to 0 out here, in that case, these vectors will be pointing in the opposite direction, from 0 to 5. Now, here, this particular elevation field, can I come up with an equation for that? It would be five R for R less than 1 for R between 0 and 1, and for R between 1 and 2, we could say it's 5, 2 minus R. Is that going to match my picture? So when R is equal to 2, and then 0 everywhere else, for 0 for R greater than 2. So it's really, increasing linearly here from 0 to 1, and with R equal to 1, it would be 5. With R equal to 0, it would be 0. And this at R equal to 1, it's 5, but at R equal to 2, it's back to 0, and then 0 at all. So it roughly matches, this figure. Can you visualize that? It's actually, if I looked at it along the x-axis here, what this is going to look like. And then this would have a height of 5. It would look like that. But it's really this circular ridge all around the origin. This particular elevation map, where I'm looking at this ridge all around me, is most conveniently described in, actually, I guess we've been using rho for our cylindrical coordinates and R for spherical. It wouldn't matter here because I'm in the XY plane. So what's the corresponding gradient? Well, we have this image of it, this mental image it's directed, it's rho directed, right? Positive rho directed here, and negative rho directed for a radius greater than 1. And then the rate of change here really is 5 feet per, 5 meters per meter. That's the change in elevation over this distance. So if I take them both to be meters. So what's the corresponding gradient in cylindrical coordinates? Well, if you look on the back of this, the gradient in cylindrical coordinates, del F, the rho component is partial F with respect to rho. That's okay. It looks familiar. And the phi-directed component is not just the partial of F with respect to phi. It's got this other term in it. Okay. And so you'll want to refer to this, the Z component, which is a different distance, is just the partial of F with respect to Z. So this is the gradient in cylindrical components. So how would we apply it to our elevation? Well, I'll just go ahead and fill it in here. Our gradient of our elevation would be, so for rho between 0 and 1, this is only rho dependent. I could have made it 5 rho cosine phi or something like that, but I just gave it circular symmetry. So it's a fairly simple field with radial symmetry. But if you look at this is the only non-zero term I'll have, right? My elevation is only rho dependent. If it were constant everywhere, if it were 5 everywhere, then this would be 0. The gradient would be 0. There is no rate of change in a constant, right? It's like taking the derivative of a constant function. So is everyone okay with that? All these other derivatives are going to be 0. Derivative of elevation with respect to phi, there is no phi term there. The derivative of F with respect to Z. The derivative of the elevation with respect to rho is just 5, but and this would be for rho between 0 and 1. It's just a constant vector pointing radially outward. Now, what about in this next region? What's the derivative there with respect to rho? It's going to be minus 5, right? I can expand that as 10 minus 5 rho, but the derivative of 10 with respect to rho is 0. So it's just minus 5. Again, that's in the rho direction. 1 less than rho less than 2. And then for rho greater than 2, it would be 0 everywhere. Okay. So it's probably about the best I can do in terms of trying to give you a rough mental picture of what the gradient is. It's a vector field associated with a scalar field. So if you've ever seen topological maps, contour maps, the gradients would be actually the perpendiculars to the contour maps. If you know what I'm talking about with contour maps. Contour maps were on a contour map you have circles at constant elevations. And then they're typically labeled, the contour, the circle would be labeled 0, and this one would be 5. But the perpendiculars to the contours are actually what we're talking about. When the contours are really close together, you get a rapid change. And then the corresponding magnitude would be the difference in elevation between the contour lines. Okay, so why is this important to us? Again, we're laying we can think about the gradient as a mathematical operator. You probably saw it in calculus and talked about it, but perhaps viewed it just as a mathematical function. Well, our big application in electromagnetics is the electric field. Here, R is not our coordinate in spherical coordinates. R here is just a position vector, so it could be x, y, z. could be rho phi z, could be r theta z. But the electric field is, it's not the gradient of the voltage, it's the negative of the gradient. So the electric field actually points in the maximum rate of decrease of voltage. So, but we'll see this in the next chapter when we talk about electrostatics. Divergence. Now, divergence does just the opposite. It's an operation we do on a vector field to get a corresponding scalar field. So I mentioned at the start of class, I walked up this morning and left my lecture notes at home, so I was trying to reconstruct stuff directly from the book, and trying to recall what I had on my lecture notes. So divergence is related to flux. Okay, so we can really talk about the flux of any vector field. And it's this dot product of the vector field with this surface. And it really gives us the amount of the vector field that's crossing this surface. Again, roughly, if I had a plane here as my surface S, and the vector field pointing in that direction, the normal to my surface, okay, so ds would actually be the vector in that direction. Here there's no flow crossing the surface, they're perpendicular angles. So this dot product would be 0. But on the other hand, I have maximum flow, and the Latin word for flow is flux. For some reason we call it flux instead of flow, but in electromagnetics. But here, that with the surface perpendicular to my vector field, so that the perpendicular to the surface is aligned with the vector field, I have maximum flow or flux through that surface. And if it's at some angle, I get some corresponding value between the possible maximum and then 0. So this is roughly what flux is an attempt to measure. The amount of, and it comes from treating vector fields as fluid fields. How much flow of the fluid field actually crosses our surface. And it doesn't have to be, when I say surface here, it doesn't have to be a physical barrier. It can be an imaginary open surface, like just a plane. Okay, but that's not a wall. Okay, it's just a rectangular opening. Could be a circular opening or whatever. But flux is an attempt to measure this flow of this vector field, whether that has any physical meaning, like if A is a fluid velocity in kilograms per meter squared, then we get the amount of fluid mass crossing that surface, for example. Surface would have area of meters, units of meters squared, so the product would give me mass. But it has meaning in other applications, electromagnetics being one of them. So this is the flux. In this case, we can interpret A as a flux density. So whatever F has, if F has units of kilograms, A would have units of kilograms per meter squared. Now that's not divergence. The divergence of the vector field is defined as the flux, the net flux through, now, I don't think I've used this symbol before. This represents a closed surface. So might be a sphere. Okay. It could be a hemisphere, but to close the hemisphere, we would have to include the bottom plane. Okay, it couldn't just be an open hemisphere, but it could be half of a sphere. And you could always think of this as some sort of solid volume, and then the surface are all the sides on that solid volume. So this is what I mean by a closed surface. And so the divergence is the net flux through a closed surface. Now, when would I ever have net flux through a closed surface if you think about water? The only way I could have that is if there's a source of water inside my closed surface and it's flowing out. Otherwise, with water, if I take any, if I take a box and set it down in the river, get my imaginary box, the amount of water entering the box is equal to the amount of water leaving. That's conservation of mass. Okay. And so the net flux through through that closed surface, and it wouldn't matter what the shape is, it would be a box, a sphere, whatever. In that case, the net flux would be 0. So this is a measurement of the amount of material produced by a source within that surface. So this will only be non-zero when there's a source, some sort of source producing this, whatever's flowing out. And again, it's easier to think about fluid. Or if there's some sort of sink inside this thing, that's inside our closed surface, that's causing the water to disappear, the fluid to be drained away somehow. In that case, the net flow would be negative. Now, and then it's divided by the volume enclosed. And then it's actually a limiting operation. It's the limit as E goes to 0. Now that would be an awful thing to actually try to compute that way. So it's equivalent to, and I'm not going to go through the proof of this. I don't think he even has it in the textbook. You can just find it in some electromagnetics text. That this is equal to the partial of the x component with respect to x, plus the partial of the y component with respect to y, plus the partial of the z component with respect to z. So again, pretty simple. Maybe even simpler, as simple as the gradient, in terms of calculation, except in other coordinate systems. And again, on other coordinate systems, you've got the definition of the gradient on your handout. Now, we can also, another way to write this is also equal to del dot f. And where does that come from? And del is this vector operator. I mean, it's a vector itself. It can operate either on scalar fields, like with the gradient, or on vector fields in the divergence. And then, of course, our F field is Fx plus y, Fy plus c, Fc. But the dot product of these, remember, to do the dot product, it's just we multiply the x components plus the y components plus the product of the z components. So again, it's not really, this is a derivative operator. It's not really a product, but it helps you remember what that is. So you'll see the divergence written in either of these two forms, div f or del dot f. And often it's just said, it's pronounced del dot f. Okay. So now one of our applications that we will see in the next chapter is that, I mean, it's been a while since we talked about the D field, which was the electric flux density, if you recall from back in chapter 1. The divergence of the D field actually gives you the charge density. It's equal to, this would be in coulombs per meter squared. So, rho v is the charge density in coulombs per meter squared, and then the divergence of D is equal to that charge. So with our surface, if we've got a surface with no charge inside it, the divergence would be 0 throughout that surface. The divergence is defined at a point. Again, with my closed surface, if there's no charge inside, talk about the flow of the D field or the flux of the D field out of that surface, there would be none. There's only flux in the D field if our surface encloses charge. But the divergence of D is, you know, again, this is a scalar field. There's no direction associated with it, but it exists at every point. So it would only be non-zero at points at which I have charge, in other words. So let's see if we can do a calculation. So, often I write the unit vector before the coordinate, and then sometimes after. He usually writes it before in the book. It's usually more convenient when you're working with vectors, because I like to put the unit vector first, and then if the component's long, it just fits in afterwards. Okay, so I'm going to give you a few minutes to find del.f. Okay, so use your coordinate sheet, your handout rather. Find. Now, the other thing I'm expecting you to kind of know is, figure out what coordinate system we are based on the letters that are being used. Okay, so X, Y, Z, that's obvious. If it's a rho, it's cylindrical. If it's an R, it's spherical. Also, we don't have a theta in cylindrical. We only have a theta in spherical. So this is spherical coordinates. We've got an R unit vector instead of a rho unit vector. Okay, that's a nasty looking expression, right, for the divergence in spherical coordinates. It's not as bad as the curl, which is right below it, which we'll talk about next time, but it's still a pretty nasty looking expression. But, you know, ask yourself, you know, you see that we've got derivatives with respect to theta and also phi, and then the AR, A theta, A phi terms are the corresponding, you know, components of this vector field. We only have, in this case, an FR component, right? There is no theta unit vector or phi unit vector, you know, nothing plus theta hat plus phi hat. So the only term that's going to survive del dot A, del dot F, is the first term, 1 over r squared, partial with respect to r, of r squared. And I see an error in my handout already. That should be a lowercase r. There, the lowercase r, it's got an uppercase r here and on the handout, but we're not using uppercase r's to represent anything, so somehow that slipped through. So this is 1 over r squared, the partial derivative with respect to r. I've got to multiply this by r squared before I take the derivative. That's what this means. So multiply r by r squared. Then now take the partial derivative, and I'll get a 3r squared cosine theta. And then finally, the r squareds cancel out, and I'll get just a 3 cosine theta for the divergence of this particular field. Again, an electric field often will we'll find if we're working in a charge-free region, the divergence of the electric field, the D field, would be 0, because it's only non-zero when there is charge present at a point. So we have some other examples there. The last thing I want to mention here is the divergence theorem. And here it is. It states that the volume integral over the divergence, del dot A. So, I mean, you make it through this course, you can call yourself an electrical engineer. If you know what all these terms mean, divergence, curl, gradient. Yeah, if you look at that, that has some meaning to you. This is an integral, a volume integral over the divergence, right? The divergence theorem says that's equal to the surface and the volume here are tied together. I talk about a closed surface, or really the closed surface is the surface around that same volume. A dot ds. So the divergence theorem says that, remember, this is flux, right? This is net flux. But the divergence theorem says the net flux is equal to the volume integral over the divergence of that field. Now, you can do either side of this, integrate either side of this equation. I'll try to find a simple example. He doesn't have one here, so I'll make one up. Let's say A is equal to, and keep it pretty simple, r hat r. So it's spherical coordinates. So this is the definition of my field. So it'd be 0 at the origin, and then as we get away from the origin, it gets stronger and stronger. The field strength increases with r. Now, my surface, and to apply the divergence theorem, we want flux, net flux through. Now, this is going to have net flux, okay, because it's 0 at the origin, and then it's just radiating outward. But the net flux through sphere of radius 2, centered at the origin. So I'll do my best to, at least try and give you some idea of what that looks like. That's about the best I can do. It's a globe centered at the origin of radius 2. Okay, that's our shape. Corresponding to that is this vector field. We want to find the flux of the net flux of that vector field through this shape. Okay. We can do that by evaluating either side of the divergence theorem. So let's do what we've been using as our flux definition now up to this point. But in spherical coordinates, on my sphere, here's where you go to the differential surface for in spherical coordinates, and I'm on an r constant surface. That's a sphere. So my ds here it's r directed, and it's r squared sine theta d theta d phi. If I integrated over all theta and phi there, I'd actually get the surface area of a sphere. Now, there is no dr component here because r is fixed on the surface. As a matter of fact, r is 2. So I'm not doing a volume integral at this point. So on the surface, r is 2. So I could call this r sine theta d theta d phi. And similarly, on the surface, you don't have to plug that in now. I mean, and I'm not integrating over r anyway. But a hat dot ds would be, and I picked a simple example here. My surface normal is in the r direction. That's normal to the surface. So it's just going to be 8 sine theta d theta d phi. So the integral over this closed surface of a dot ds is the integral, I'll pull the 8 out, of sine theta d theta d phi. So remember, theta goes from 0 to pi, phi goes from 0 to 2 pi to sweep out this entire surface. Well, there's no phi component of the integral of the integrand, so I can split that out like this. So this is going to be 2 pi times 8. So this is going to be 16 pi. And then the integral of sine is minus cosine. Evaluate cosine theta at pi, it's -1. So I've got minus and -1, so I'll have 1 minus a negative. Okay, so that'll be plus, evaluate cosine theta at 0. It's going to be 2. So it looks like this is 32 pi. In this case, it's not a terrible problem, but it was a bit of work to get there. Now, the divergence theorem says that this is equal to the volume integral over the divergence of this field. So often, this is easier to evaluate than the corresponding surface integral. So here I'm going to have 3 components here to my volume. I'm going to integrate over r, theta, and phi this time. But hope this may be simpler if the divergence turns out to be particularly simple. So look at now the divergence in, is this the same one I did earlier? Not quite, I had cosine theta over there, didn't I? So this is going to be 1 over r squared, partial with respect to r, of r squared, and then the AR component is just r. So it's going to be 1 over r squared, partial with respect to r, of r cubed, or 1 over r squared, that's going to be 3r squared. This just becomes del dot f. Right. So, shoot, I'm sorry. Using F here for flux, and somehow my field is actually A. Looks like I did okay there. My field is actually A. F is my flux of this A field. So I had both I was using the capital F to represent flux, and then I somehow, in a lot of, and what I was writing over there is also using F as just a general, F bar is a general notation for a vector. Well, in this case, the flux, del dot A over the volume, actually becomes, this is a triple integral because it's volume. And the dV, differential volume, in spherical coordinates is r squared sine theta dr d theta d phi. And here, r is going from 0 to 2, theta is going from 0 to pi, and d phi is going from 0 to 2 pi. Now, r is not fixed here. I'm doing a volume integral over the inside of the sphere, so r changes. It is still separable. So 0 to 2 r squared dr, 0 to pi sine theta d theta. And 0 to 2 pi of d phi. Okay, so this is going to be 3. Integrating that, I'm going to get 1/3 r cubed, evaluated at, I'll write it down, 1/3 r cubed, evaluated at 0 and 2. Here I'm going to cheat. I already did that one. It was 2. So this next one becomes 2. This last one becomes 2 pi. Okay, so this is going to be my 1/3, 3 times 1/3 is going to cancel out. So this is going to be 8 times 2 times 2 pi, which is 8 times 4, or 32 pi. We could argue about which one of these was actually easier to evaluate in this particular example. Yeah, but often as we're working through these problems calculating flux, where did the result go? One side or the other here may be easier to evaluate. So I gave you a homework problem similar to this where you have to evaluate both sides, okay, and verify, like, according to the divergence theorem, doesn't matter what type of field A is, the divergence theorem says those two intervals should be, the volume interval or the divergence is equivalent to the flux. There's another way to get the flux. Okay. That is it. Did everyone get the handout?